Welcome to video lecture on BJT working as a switch, or it is also called as an inverter. So we all studied that BJT can be worked as a switch or an inverter when it is biased in two regions. Either it is in saturation region or it is in cutoff region. If BJT is in saturation region, the base emitter and base collector junctions are forward biased. If the BJT is in cutoff region, the base emitter and base collector junctions are reverse biased. Today, in this video lecture, we are going to understand the working of BJT as a switch with respect to an example. So this example is as shown in circuit. And this circuit is, BJT circuit is in common emitter configuration. So now let us understand what are the components are connected in this circuit. Basically an NPN transistor is considered in this example. And now this is biased in a fixed bias mode where emitter is directly connected to ground. And you have a base resistor RB and you have a collector resistor RC. Now an input variable DC supply voltage VBB is connected to the base of the transistor through RB resistor 65 kilo ohms. And the input voltage is varied between 0 to 5 volts. Now at the output side, the supply voltage known as VCC is connected to the collector of the transistor through the collector resistor of 600 ohms. Now we are finding the output voltages through input and output loop equations. So now let us first consider the case 1 where the input VBB given to the base of the transistor is 0 or less than 0.6. And we all know that for a transistor wherein base and emitter part of the diode in a transistor has to be working, means the base emitter junction voltage has to be 0.7 and more. But the supplied input voltage is now less than 0.7. Since the supplied VBB input voltage is less than 0.7, there should not be any base current at the input side of the circuit. So now we'll see what is an input loop equation when the input voltage is 0 or less than 0.6. So here an equation we all studied, an input loop equation IB is given as VBB minus VBE divided by RB. So this results with the IB as 0 microamps. When the input current is 0 microamps, the output current also is going to be 0 milliamps with the equation beta times of IB. So now here at the input side, the input voltage is 0 or less than 0.6 and the input current, which is IB, is 0. So under this condition, what will be the VBE biasing voltages? So VBE, the junction base emitter junction, is now reverse biased. So what did we understand now with the circuit? At the input side of the circuit, when the input voltage is less than 0.6 or it is 0, the input current is 0. So due to this, the biasing voltage which is applied at the base emitter junction is less than the 0.7. That's why the junctions are reverse biased. Now, for the same input voltage, which is 0 or 0.6 volts, the output loop equation is written as VCC minus IC into RC minus VCE is equal to 0. And now with this, we can find the VCE voltage as we can find the VCE voltage as 5 minus beta times of IB, which is nothing but IC, times RC will give you 0 drop. because IC is 0. And finally, our output voltage, that is voltage across collector to emitter voltage, is same as the collector voltage because emitter voltage is 0, which is also same as the output voltage V0, which will turn to be 5 volts. Now, we have seen this first case where the input voltage is coming to this graph, the graph where we can understand when the input voltage is less than 0.7 in this area, output is going to be 5 volts from the output loop equation. So I'm showing here 5 volts. So now you compare the input voltage Vi or the input side of the junction, that is base emitter junction, which is already reverse biased, and also with respect to the output voltage 5 volts, you compare base collector junction. So now base collector is, what is the voltage at the collector? It is 5 volts. And what is the voltage at the base? It is 0 or 0.6. So which is also making the base collector junction reverse bias. So now what did we see with these two values are, when input voltage is 0 or 0.6, even less than 0.6, the output voltage goes to 5 volts. Now, when the output voltage is at 5, the base collector junction is going to be reverse biased. When the input voltage is at 0, the base emitter is going to be reverse biased. So now you are exactly in the cutoff region where both the junctions are reverse biased and the input current is also 0. So under this condition, where both the junctions are reverse biased and the output voltage is at 5 volts. And this is the region where in this graph I'm trying to show 5 volts and here we can see that there is a vertical line with the voltage of 0.7. Any voltage, input voltage, which is an horizontal input voltage, less than 0.7 will make the output voltage 5 volts and keeps the transistor in cutoff region. So this we call it as a cutoff. Fine. So this region we call it as a cutoff region. Now we'll study this second case where the input is increased more than 0.7. This, okay, in the graph. Now when I increase the input, assume I have increased to 5 volts. Obviously VB will be at 0.7. The junction of the base emitter is having 0.7 voltage. Now with this, what I'm going to understand here is that when I calculate the base current with this input loop equation, so I get around 66 microamps. And with that, the collector current would be, it is the collector current is 8.27 milliamps. Okay. So now, for the same case where input voltage is 5 volts, we need to write an output loop equation. So we know that output loop equation is VCE is equal to VCC minus IC into RC. Now you have 5 minus IC is 8.27 milli multiplied by 0.6K. So what is this value is? Nearly you are getting VC is equal to 0.038 volts, which is equal to the VC voltage, which is also is equal to V0 voltage. So V0 voltage is the collector voltage with respect to the ground, or it is also collector to emitter voltage, where emitter is at ground. So now what is the condition case 2, where we apply the input is equal to 5 volts, whereas you got output is equal to 0.038. Now, if I plot these two values on the graph, so now what is happening? Now, okay, before that, we'll also understand the biasing of these two junctions. Now, what is the biasing voltage in the case 2 at the base of the transistor? We know that VBE is equal to 0.7 and which is equal to VB. And what is VC is nothing but 0.038. Now, when you compare base to collector voltage, at the base side it is 0.7 and at the collector side it is 0.038. So the base collector junction is now forward biased, because base being the P side and collector being the N side of the transistor. So N side of the transistor is less voltage compared to the P side of the transistor. So it is forward biased. Now, looking at the input side of the same second case, where the input base is at 0.7 and emitter is at 0. So your base emitter junction is also forward biased. Now under case 2, looking at the input base emitter and base collector junctions, where BJT is now in saturation region, where both the junctions, base collector and base emitter, are forward biased. So now we'll plot these values on this graph. As the input is varied beyond 0.7, you should get a decrease in the V0. So it is slowly decreasing. And now, since the transistor now is entered into saturation, so you know that in saturation, IC current is always varying very slowly. So even the output also varies very slowly when the transistor enters into saturation, as Vi is greater than 0.7 and above. So now this part where the current is varying very slowly and output is also varying very slowly and slowly reaches to 0. This part of the graph, we call it as a saturation, where both the junctions are forward biased, where this is the part of the graph, this part, where slowly the output is decreasing. At any particular point, if you take, there will be a constant voltage of V0. And this is the point of active region. So now, if you look at this graph, the cutoff is having a voltage of 5 volts, whereas current is 0. And if you look at the saturation, the current is maximum, whereas the voltage is minimum, output voltage is minimum. Here, if you see, the output voltage is varying very slowly, the minimum. So this region, we call it as a saturation. So now, if we take both the cases, the case 1, when the input is 0, output was 5 volts. When the input was 5 volts, output was 0, nearly 0.038. So this working of the BJT between cutoff and saturation shows that BJT is working as a switch, or it is also called as working as an inverter. So this is all about the BJT working. So we'll meet up in the next videos on CMOS, inverter and NAND NOR gates. Thank you.